512, I think that's what it was. What's in there? Better like this. Well, naturally, it has a good base. We treat certification badly because the number of tests is off the scale. It will be comparable with the cost of this very development. So it is a sore point, let's say. We certify only because we have a database from the 30th, a wooden propeller from an airplane rail. They got wood, glue. It's not like it's a monolith. Not just because of that. Wooden propellers don't require life testing. As for strength, it's just torn, twisted in tube, and that's it. And all those resource tests, which, well, Euroman says that the screws, which many make, he said, what kind of screws they are? Circus. They did not even reach the pipe. They collapsed before the pipe. As for titanium, the situation may be different now. To make a titanium part, you have to order the development of mines 5 years in advance so that you get the right amount of titanium in 5 years. So it's scheduled down to a kilogram. Well, we'll make it out of slab. You don't have to stand in line if you have slabs. I think you can make one of this in aluminium. The resource is much less. It accumulates fatigue faster. It can take up to a month to buy something. Why don't we just take the design to the Aviation Institute? Why should we buy something there? We'll buy it ourselves somewhere. It's very good to have a designer sitting right here and a worker standing across the building. All these issues are solved much faster. And in any case, there are a lot of them when creating something that one person has drawn and the other is making. There are always some inconsistencies. That's where the documentation can be corrected. Will you make me a pass to the Aviation Institute? Only when you sign the contract, otherwise come and visit us. The second gondola is unmanned. It must be made and designed as well. There is also the tooling, propulsion system, radiators, fans, I don't know, tanks, fuel system. The fuel system will be out of the way. We want to put it under the shell, behind the nacelle. So he's drawing here. He starts drawing the transmission. Here's the clutch, although I've got an old version. It's going to be a centrifugal clutch or not? No, it's just an elastic coupling. Just an elastic coupling. Are these gearboxes to make or off the shelf? These ones. These gears are off the shelf. We'll design the assembly ourselves. Now we'll be testing spiral antennas to communicate with the stratospheric probe at minimum power. Here they are. These are the 2.4 gigahertz. One will go outside with me. The other is pointed out the window down here. There's a spiral antenna on the receiving end and on the transmitting end. I'm going outside now and I'm going to... We're in radio contact. We've got a walkie-talkie right here. Artyom will tell me when the picture will or won't go away. And I'll go to the next subway station. You'll keep an eye on that. The goal is to transmit full HD video to the maximum distance. There are actually two antennas here. One spiral, the other one is Harchenko. I will now run outside. We'll check how much range they have, the range of communication. Then we'll go to the field and test all of it properly. Now it's just, we'll just see. WiMAX frequency is 2.4 gigahertz. Now the power is 100 milliwatts. There will be, here's the camera by the way, 150 watts. So there's two channels here, it's going to be 150 watts, but right now we're going to test at the minimum power. Okay, this blue one here is the rechargeable battery. It's going to fly on our probe. It will last for about 3 hours of operation. That's 300 watts per hour. This is a GoPro. This is a transmitter from DJI, but we are going to have it with an amplifier and a spiral antenna. I'm going to go outside now. And you're going to watch the video transmission here. You're going outside, aren't you? Go left then. Go to the barrier and then right there across. Across. Great picture. You know what you should do then? Go along Bolshak Akademicheskaya Street. Don't go into the building. We know that it catches well. The building cannot block the signal. Well, it's bearable. Don't go behind the building, behind this one. Go to the left towards Peterочка shop, in that direction. Because there are no such obstacles there. Okay, it's frozen. It's gone. Everything is gone. Gray screen. No, it's back, it's back. It's back now, great. So you went behind the building, right? Yes, there is a picture. Here we have the stratospheric probe control system, which consists of a console from which you can send up to 5 commands to the flying machine. There is a Karchenko antenna connected to the console and a spiral antenna. The spiral antenna was made by ourselves. It is made according to a certain technology. The antenna has a certain design, so we're testing it now for successful reception. Now Dennis has gone outside our building and is transmitting the signal from the same spiral antenna to our receiver. Okay, I'm back. The quality was great, by the way. And when I came in the building, it was great as well. The valve will be... Here's the thing. Here you see the 2-arm one. And here you get this dependence. It turns out that this more complex one with 2 rockers, that is, there is a pressure difference when it changes. That is, the force increases from the inside. And depending on the angle of this one, as it is initially set up, it can have a different characteristic. It can open linearly, or it can, like, it goes to 45 degrees. There is like a pop, that is, it changes force. To change by force. It's done for this purpose. The valve that I will develop will be on an airship that will be launched into the air in a year. It will be made entirely on a 3D printer. Fit all purposes, all weather. I decided to make the fan hollow. I think it is possible to save money on materials. The spring can be adjusted, so the air tightness is only here when we drive in. Well, how do we put the spring on? We put it on this rod here, and we plug it. Plug it with a plug, which is on screws, roughly speaking. Can you show me the whole thing together? I can do it in a different section. No, just show me the bottom more. Right now. Maybe just like this. It's great now. We're gonna have to seal it here. Now we're gonna have to seal it there because it is collapsible. Got the threads right here. But you can put a rubber band in, basically. Now, this routing doesn't make any sense because it's a sharp corner. It has to be from infinite space into the channel. It has to be a round radius so that the resistances don't get very dynamic. I just had this crazy idea to put our fan on top. That's how we're going to have it. We'll have to think about it a little bit more. We don't need access to those screws, do we? No. We just screw them, that's all. It's gonna be different. First of all, what can we do? we can make this flange smaller. The flange will recess too, it won't stick out past that size. It'll even be recessed a little bit more. Even the nuts won't stick out beyond that size. The air gas system is one of the main systems of a soft shell airship, because it is the system that is responsible for making sure that we have the shell always in a fulfilled state, and that we always have the pressure inside the shell within the specified limits. Some of the main components of the air gas system, apart from the sensors, tubes, and everything else, the power supply, it is a valve that relieves excess pressure and a fan that builds pressure if it drops below a predetermined limit. The fan is required to have high output and high pressure. And all this has to be crammed into fairly modest dimensions. So we go for high rotational speeds to get the pressure and performance. It's quite a high-tech product, especially since we've now decided that we want to print it entirely in engineering plastic. Well, this is roughly the kind of fan we're discussing. Only it's a fan from, say, a very small unmanned airship. Here, let's say that the diameter of the impeller itself is only 70 millimeters, and the characteristics are modest because it is installed on a shell of about 100 cubic meters. And we're now designing the same fan. It turns out it is 3 times the diameter, which will be installed on a shell of 2,000 cubic meters. Well, Sergey, I guess we'll have to do it a little bit differently.